Hi. My name is Wietse Venema, and I'm an engineer at Google Cloud in the serverless team. And I'm here today to tell you a bit about WebAssembly beyond the browser. So in the recent CNCF 2022 annual survey, there was this key finding. Containers are the new normal, and WebAssembly is the future. Well, that's a bold, forward-looking statement, and it certainly got my attention. So, here's the vision of that future, right? So we moved off of hardware to VMs. We started packing our apps into containers to run them more easily. And then the VMs started to disappear because we got tools like Cloud Run on Google Cloud and Fargate on AWS that abstract away the details of the infrastructure that the containers run on. And now there are Wasm modules, right? They are smaller, more efficient, more secure, and they can be instantiated in milliseconds instead of seconds. And that enables radically new execution models and pricing models. So my mind went straight back to 2009. I was working at a small internet services company here in Utrecht. And one of my colleagues went to JSConf, and he learned about this new thing, and it was Node.js, right? JavaScript on the server. and he was like extremely excited about it, and he kept telling me that this was a really, really good idea. And at that time, I thought it was ridiculous, because why would you run JavaScript on the server, right? But this is the time where we were building websites for Internet Explorer 6. I would write my Java, deploy it to JBoss, right? And JavaScript, that's like Scriptaculous prototype JS. And everything that on the server, like all the libraries didn't work because they were built for the browser, not for the server. But look where we ended up today, right? JavaScript on the server is a huge success because some folks at that time saw unique abilities of Node.js and adopted it. And over time, the developer tooling and the ecosystem developed further. But let's take a step back. What is WebAssembly? So you run WebAssembly modules in a WebAssembly runtime, which is originally designed for the browser, but you can run it on a server too. And a module is a binary instruction format. So that means that those modules are portable across CPU architectures. Like Java developers think, hey, this story sounds familiar. But WebAssembly is different. Modules run in a sandbox with a clearly defined API between the runtime and the host. So this is how that looks like visually. So you run a Wasm module using a Wasm runtime. And in the browser, Wasm is often used to increase performance, right? People they run 3D engines in Wasm because it's way more performant than using native JavaScript. And recently, someone figured out how to run the entire WordPress stack in the browser. So that includes PHP. So it's WordPress Playground. You can access it. You get WordPress. You can install plugins. They use SQLite instead of MySQL, but it works. It's in the browser. So there's a lot of innovation happening there. And on the server, the execution model looks very similar to the browser, but there is a way wider diversity of runtimes. Now let's look at a text-based representation of a Wasm module. And this is a trivial one. There's one function, and it adds two numbers. So there's a function signature with two parameters and a result. And in the function body, it takes those two parameters and loads them on the stack. And then in the next instruction, it's the add instruction. It takes those two parameters from the stack, adds them together, and leaves one result. The remaining element in the stack is the result. And a function may be exported, right, to the runtime. And functions can also be imported from the runtime. And this is important because this ties into how WebAssembly models are sandboxed. I will get back to that later. But for now, remember that a runtime takes this instruction format and runs it on a stack-based virtual machine. But let's do a demo now. Can we switch to the Yes, I'm already there. Awesome. So here's the same text-based representation of a Wasm module with just one function, and I export it. Now, what I can do is I can turn that text-based representation into a binary Wasm module. There's this tool, wat to Wasm, lets me do that. So I give it the add.wat, and look, a Wasm module appears. Now I can, my laptop is a server, right? So I will use a runtime. Wasm time is a popular runtime built by the Bytecode Alliance. I will take this Wasm file and execute it. Nothing happens because I didn't invoke the function. So I will invoke the function, add, and I will ask it to add 1 and 2 together. It should be 3. What it gives me is a bunch of warnings that arguments to functions is an experimental feature in the CLI, but it also gives me the result. I also have one that doesn't export the function. And if I compile that, add no export, and I run it, add no export.wasm. I try to invoke a function, but it says no export found, right? So there's this contract between the runtime and the modules. You do that with exporting and importing functions. Can we go back to the slides? Bob. Can we go back to the slides? Thanks. Yeah, so to wrap up, I compiled my text-based Wasm module to a binary Wasm module and executed with Wasm time, which is one of the many Wasm runtimes. And I executed the module and invoked the exported function. I know. You're probably thinking, wow, that's exactly what I need. Editing text-based WebAssembly, assembly code. I'm sure this person on stage enjoys this very much, but it's not for me, right? By the way, if you do enjoy writing assembly, there is a workshop today, this afternoon, and you can learn how to write assembly for the 8-bit Nintendo, the NES. Like, I'm told it's a really awesome workshop. But hey, for your day job, it's likely that you don't want to write WebAssembly by hand, and instead use a higher level programming language like Go, Rust, or C++. And for those languages, a Wasm module is just another compile target. And this picture will look different for interpreted languages like JavaScript and Python, but I'll get to that later. Another important thing to realize is that this means that Wasm modules are portable across CPU architectures. The same module literally runs anywhere. We've been telling this about containers forever, right? Containers run everywhere. But like the minute people got those M1 Macs and started to build their containers on their local host and deployed them to a server, then the containers didn't even start because it was compiled for a different native CPU architecture. This is ARM, and most servers run x86. So Wasm modules are more portable than containers. OK, so Wasm code runs in a tightly sandboxed environment. All the code that runs on that stack-based virtual machine can only interact with that virtual environment. And to access, well, useful things like file systems, networks, hardware clocks, heck, even make HTTP calls, Wasm modules require you to explicitly export functions to and import functions from the runtime. But luckily, that doesn't mean that you need to reinvent the contract between a module and a runtime for every application you build. That would be very impractical, because that would also mean that every runtime would be completely custom for your application, because you need to figure out this API. So the WebAssembly System Interface standardizes this API between modules and the runtime. And now, what is exactly in this contract? This is all a moving target, right? We're at preview 2, which isn't finalized, and most programming languages now support building to preview 1 WASI binaries. So this lets you read and write files, like in the sandbox by the runtime. Things like program arguments, environment variables, the hardware clock, because it's useful to know what time it is, random, and there's limited support for sockets. So now you're thinking, okay, wait, this means that I can't start an HTTP server and listen for incoming requests and handle them? It's experimental. And oh, you can do outbound connections. So that's why there's now a preview too, which solves a few of those things. But let's make it a bit more practical and switch to the demo again. I have a different file. That's my hello world. It won't go any deeper than this, I promise you. So this is Go code. It will print hello world. I usually do go run main.go, and it tells me hello world, and I'm happy. Or I compile it to a binary, and I get this native binary. I execute, and I get hello world. But you guessed it. I will remove it because otherwise it's a bit weird. I can also build it. So here's what I'll do. I use a different compiler, not the Go standard one, because that will only build WASI binaries for me in August 2023, and that's not today. So I build my Wasm binary. I target WASI as the system interface, and that's great, because that means I can actually write the standard out. So I have my hello world.wasm file. I run it using wasm time again. And lo and behold, hello world. We need to, doing demos is incredibly scary. And software, right? You miss one semicolon, and everything breaks on you. So I need a bit more encouragement if I actually succeed in those things. I did try to keep them very safe and simple. But anyway, back to the slides, please. So my hello world program prints hello world to standard out. I compiled my hello world program using the TinyGo compiler. That's because the official Go compiler can compile to Wasm, but only supports web targets and not WASI. We'll start with Go 1.21, which comes out in August 2023. And WASI defines this fd-write function that provides access to the standard out. So that's why this demo worked. So here are the benefits I've talked about so far. There's binary portability across CPU architectures, language independence, near native performance. Like another pattern that people use is they'll take a Wasm module and they compile it to native code on the host they run it on. So you get native performance. And there's a very strong sandbox, maybe a bit too strong. Like if you expect your software to work unchanged, like we had with containers, that's not the case with Wasm. So given these benefits, can I do something interesting? Can I build my own functions as a service platform? So let's find out. This is what I have in mind. So I have this website, right? And as an admin, you can upload a Wasm module. And my Wasm as a service then stores that module file in the cloud storage bucket, and it returns a unique endpoint to the user. Like find your function, your Wasm function at /hello world. And then the next step is, hey, am I going to invoke this function? So I send a request to /hello world. I retrieve the module file from cloud storage. I'll execute the module in a Wasm runtime, and I capture standard out. And I return the response. So let's see if I succeeded. Can we go back to the, yeah, thank you. So let's take the hello world one. Right, so this was where I wasm time hello world, and I got hello world back. And here is my competitor to AWS Lambda and Cloud Functions. That lets me Wasm as a server.web.app. Please don't break my site. So I dropped the binary here, and success. Like, don't comment on my web design skills, please. Hello world. Hello world. It worked. Yes. But this is a boring demo, right? I have better demos. Like Hello World is so mundane. I also have unicorn confetti, right? So go run main.go, and it will return a bunch of HTML, right? Sprawling unicorns. So all I have to do is turn it into a Wasm module. I target WASI, and then I upload that one. Oops. There you go. Unicorn confetti. Oh, no, that's download. There we go. Oh, I keep not hitting the drop zone. I made it so big. Yes, it worked. Yay! OK, cool. Now we can go back to the slides. I bet you want to know how I implemented this invoke endpoint, right? So I'm going to take you through the function that executes the Wasm module after downloading it from cloud storage. I wrote my app using Go, because that's a programming language I'm very familiar with. Let's start at the top. The parameters here are the request context and a byte slice with the Wasm module in it. And I start with creating a new runtime. And instead of Wasm time, I used WA0. I don't know how to pronounce that. WA0 this time. And it's another Wasm runtime, but it's written entirely in Go, and it doesn't use external dependencies. So as the second step, I allocate two buffers, one for standard out, one for standard err, and I wire them to the config of the runtime. And I also tell the WA0 runtime to speak WASI, because I want to capture the standard out. And I expect my Wasm modules to be targeting WASI as an interface between the runtime and the host. And finally, I start the module, capture standard out and standard err, and return from the function. That's it. So you can build your own Wasm as a service app tomorrow. But is this even safe? Like I'm allowing users to upload untrusted code on my website. But remember that Wasm runs in a sandbox, so users can't run malicious code. Their code can only manipulate that stack-based virtual machine, like the runtime. And you only use the provided imports from the runtime. So if I don't choose to open up anything else than writing to standard out, that's all they can do. So don't even think about calling an external URL. I would need to provide an external, a separate import for that from the runtime. And also note that this is a demonstration, not real software. We have other people for real software. So after this demo, I think you have a pretty good and basic understanding of what Wasm modules are and how you can use them. I didn't show you much about the challenges. That's for later. But let's look at a few existing successful deployments of Wasm modules in the real world, because just Hello World and Unicorn Confetti isn't going to be of much interest, right? So here's Shopify functions. They let customers customize how Shopify behaves using plugins, right? User request comes in, and they want to apply a discount based on business rules. So they let their customers upload untrusted code as a Wasm module, and their architecture looks suspiciously similar to my Wasm as a service demo, because a request comes in, they run a Wasm module, provide the input over a standard in, it's just a JSON file, and the Wasm module reads the input and outputs it to the standard out. And they take the JSON and they apply the action. And they even run it on incoming requests. And another thing they do is they compile ahead of time. So my runtime was like interpreting, reading the binary Wasm file and doing it, and they generate machine time ahead of time to make sure that it's really fast, native performance in production. Second example, I have 4 of them. Second example is Envoy, right? Envoy is an open source edge and service proxy. And users can extend proxy behavior using Wasm modules. This is another plugin example. And this time, the API between the modules and the runtime is defined by proxy Wasm, which is a more it's a list of functions that's more tailored to the proxy use case. So you get, here's an incoming HTTP request with content. Do you want to do something with it? What's my next action? Like that's the proxy Wasm interface. And the reason why they adopted Wasm in Envoy was because they learned they could run it in the request path without a large performance hit, right? So HTTP request comes in, the logic runs, they forward the request or take the next action. So Wasm can be very fast and offer near native performance. Use case number 3 is Fastly. They have a compute at edge product. And Fastly is a CDN, Global Content Delivery Network. So they have servers all around the world, probably very close to me, closer than my origin server. And they let you run Wasm modules at those edge nodes, very close to the user. So they also compile to WASI Wasm modules, and you use they also provide additional services. So you have a geolocation API and a config store and a key value store. So you can implement things like rate limiting. And again, it looks very similar, the architecture, to the Wasm as a service demo that I gave. So far, I told you about 3 plugins, but this is different. Fermion Spin. This is about microservices, right? You run an app, you handle HTTP requests, you connect to Redis or MySQL, PostgreSQL. And you can run their services on the Fermion cloud. And this is how the code looks for Fermion, right? So if you're not familiar with Go, this is not how you would regularly create an HTTP server, right? The code runs on init, so they execute this microservice on every incoming request, like very similar to my Wasm as a service demo again. So they chose to run the code in init and not in main, and then you have to use the Spin SDK to get access to the HTTP request and to reach out to Redis. So let's get to programming language support. So there are a few languages that have good support for Wasm and WASI. So that's the compiled languages, C, C++, Rust, and Go. And I say good support, but in Go, reflection is not supported. So I tried to use JSON, but it uses reflection, so I couldn't use it. So I had to use the JSON library instead. I tried to use the HTML/template, but it also uses reflection, so I couldn't use it. And I had to use a different compiler because, well, Wasm and WASI, it's a moving target, so the official Go compiler is a bit behind, and it's catching up, right? There's this new release coming in August 2023, and we'll support compiling to Wasm, but exporting functions from Go to the runtime is not supported in that first release, right? So it's clearly still in development. And then there's the languages that have emerging support for Wasm and WASI. So that's JavaScript, C#, Python, Ruby, and Kotlin. And there's a few interpreted languages, JavaScript and Python. And how they will support Wasm is they will compile the runtime to Wasm and then run JavaScript. So I think there's a Node.js build or no. I think it was, I can't remember, SpiderMonkey maybe. A Python runtime, you compile it to Wasm, and it will run your Python files. Kotlin is working on a native implementation, and they started very recently. No support, Java. I'm a recovering Java programmer. So let's look at the WASI roadmap. So the initial approach was to define this POSIX-like API, where the standard Unix concepts like file descriptors, output streams, signals, they're exposed to Wasm applications. Like the idea was, like maybe we can get to a point where you don't have to change how you build, how you write your application, and like Wasm is just another compile target for you, and nothing has to change. But like the sandbox concept is so strong that they decided to take a different approach, and they now launched Preview 2, where you'll get higher level functions. Like if I was the serverless platform, my runtime would expose, handle incoming HTTP requests and send outbound HTTP requests and logging, for example. So that's way higher level than low level, hey, everything is a file or a socket. And that's a very interesting direction. But it also means that in the future, Wasm apps will look different from normal apps. So trade-offs. Should you, like, when do you use Wasm today? I think it's very early days today. Like, programming language support is improving. It's centering on WASI Preview 1. But already, people today are using Wasm modules to build interesting things, right? Because some use cases, they need the unique capabilities of Wasm. Portability, security, running untrusted code, near-native performance to run inside of the request path if you're building a proxy. They've adopted Wasm and they're successful with it. So if your use case looks similar to those, like you want to run logic in the request path, you have a proxy use case, Envoy, Fastly, Cloudflare, they had a similar use case. Maybe Wasm is something for you. Or you want to build something to run plugins, and you want to run untrusted code, like Shopify and the other examples that extend product. Like Microsoft Flight Simulator, they released the new, like the Mira plane. That's a Wasm module. So I think in the future, microservices might also be part of those successful use cases, but, well, not today. Unless you want to like adopt the bleeding edge and know that the WASI standard is still a moving target. And at moments like this, I always think back to my friend in 2009 who was very excited about running JavaScript on the server. And I kept deploying my jars to JBus, and I didn't pay much attention. So the thing I'm saying is, I think that's where we might be today with WebAssembly. So some vendors and companies are starting to embrace it for its unique abilities, and I'm hopeful that that will lead to more adoption and improve the ecosystem and the standardization. Well, that's it. Thank you. If there's